So in this presentation, we're going to continue talking about drawing Lewis structures. And we're going to focus on hypervalent species, right? These are species where the central atom has more than 4 electron regions. Okay, so in order to have these, right, one thing we know is that the central atom must be in the third period or lower. That is, the N for its valence electrons has to be 3 or greater. Because if N equals 3, then we have S's, we have P's, and we have d orbitals. So we have space around that atom for more than 8 electrons. Right? So in order to have a hypervalent species, the central atom has to be in the third period or lower, right? Because we need that d space. Now there is controversy about hybridization when we reach these hypervalent species. Right? And actually, if you ask the physical chemists, they would say there's no controversy. Right? With S and P combinations, right? You can say, okay, we're gonna take our S and 2 P's, we're gonna add that up, and then we're gonna divide that by 3, and we're gonna get 3 sp2 combinations. And that mathematical trick in quantum mechanics works because that gives a good approximation for the energy of those electrons, right? That same kind of combination, right? Mathematical combination of the wave functions doesn't seem to work with d orbitals, right? And so we can't really say that d participates in the hybridization because we can't make the same kinds of predictions we can with S's and P's. But in this case, we'll go ahead and act like we can. Right? We'll act like it does work, because I think invoking the D's is a good reminder that the D has to be available in order to accomplish these hypervalent bonding systems. Okay? So we're going to invoke it in our systems up to 6, right? Our standard hypervalent species, right? Just as a reminder that the D's have to be available for us to do this. So let's look at phosphorus pentachloride, right? Phosphorus has 5 valence electrons. 5 chlorines have 35 valence electrons. That gives us a total of 40. If we put the phosphorus in the center, 1, 2, 3, 4, 5, that accounts for 10, leaving us 30, and that lets us put 6 around each chlorine. And we're out And so there is a hypervalent species, right? So what's that going to look like? Okay, so if we put our phosphorus in the middle to get 5 groups as far apart as possible, it will assume a trigonal bipyramidal geometry, which would be a chlorine up and a chlorine down, one chlorine in that plane, one coming in front of the page toward us, one going behind us, right? Behind the page. So the bond angle between these chlorines is 120 degrees, and the bond angle between these chlorine phosphorus bonds is 90 degrees. Okay? So that is the trigonal bipyramidal geometry. And now, right, since we have 5 bonding regions, right, if we have our 3s, our 3,3ps, our 5 3ds, in order to get enough bonding regions, we have to have 1, 2, 3, 4, 5. That's taking the S, 3 Ps, and a D. And so traditionally, that's the way we would express the hybridization. Now we deal with sulfur tetrafluoride, right? Sulfur has 6 valence electrons. 4 fluorines would be 28, giving us a total of 34, right? If we draw the connected structure, right, that gives us, right, we've accounted for 8, leaving 26. And so now we start distributing those around the fluorines. Right? So when we distribute those around the fluorines, 6 goes around each fluorine. That took away 24, but that still leaves us with 2 electrons, 2 valence electrons to distribute. And so those 2 valence electrons, the sulfur is the only thing that can accommodate more electrons. So again, we have 5 electron regions. And we know that 5 electron regions try to assume a trigonal bipyramidal structure. But how does that work when one of those is an unshared pair? So here's how it would look, right? The place where that unshared pair, remember, the unshared pair will squeeze closer to the sulfur because there's not an atom over here to keep that electron density spread out. So an unshared pair needs more space than a sigma bond. And the place where it can get farther away from things is on the equator, right? And so we call this kind of arrangement a seesaw, right? Now, it may not be easy to see here, but let me redraw it. Right? So here it is redrawn, just tilting it over, and we can see here are the legs of our seesaw, here are the seats of our seesaw, and we can imagine, 2 atomic size elves being able to sit on that and ride those seats up and down as it tilts back and forth. And so that's where the seesaw designation comes from. And again, if we were going to invoke the classic hybridization pattern, right, we would say that this is sp3d, right, that we would need 1d to get the 5th region of electron density that we need to accommodate the bonds and unshared pairs around that central atom. With iodine trifluoride, right? Iodine would give us 7 valence electrons. 3 fluorines would give us 21. That's 28. And so we can draw our connected structure. Right? So there's our connected structure. That accounts for 6 electrons, leaving behind 22. Now we can start distributing those around the fluorines. There we were able to put 6 around each fluorine. That's 18 more electrons, but that leaves us with 4 that we need to distribute. The only place they can go is on the central atom. So we have 3 bonding pairs and 2 unshared pairs. So here's a representation of what that would look like. Again, the unshared pairs are able to stay farther away from other regions of electron density if they're on that trigonal equator. If we quickly redraw this in this relationship, right, you can see why this is called the T-shaped structure, right? So the overall electron regional geometry is still our trigonal, bipyramidal, but the bond geometry leaves it as T-shaped. So here we have Xenon Difluoride, right? Notice xenon is a noble gas, but it can form a compound with fluorine, right? So xenon would contribute 8 valence electrons. 2 fluorines would contribute 14. That leaves us with 22. Minus the 4 from the bonds leaves us with 18. We start distributing around the fluorines. Right? So there is 12 electrons distributed around the fluorines. That leaves us with 6. The only atom that can accommodate the extra electrons is the xenon. And so we would put those on there as 3 unshared pairs. Again, we still have 5 regions of electron density, right? This is our trigonal bipyramidal structure. Right? But when we draw the molecule, we get this kind of structure where the 3 unshared pairs are all around the equator, and the molecule ends up being linear. Now with sulfur hexafluoride, right? Sulfur gives us 6 valence electrons. 6 fluorines gives us 6 times 7, which is 42. That's a total of 48. So now we have to draw our connected structure. So if we make 6 bonds to the sulfur, each of those bonds counts as 2 electrons. We take away 12. That leaves us with 36 to start distributing from the outside in. So there, when we put 6 electrons around each of the 6 fluorines, that's 36 electrons, leaving us with none, and we have a central sulfur atom with 6 regions of electron density, right? That shape is octahedral, right? Now, how would we draw that? A way to represent that is here, right, where the bond angle between any 2 adjacent bonds is 90 degrees, right? We're 90 degrees there, we're 90 degrees there, we're 90 degrees there. Okay, so all bond angles are 90 degrees. And since we've got 6 regions, if we're going to go to the classic hybridization description, right, we would have S's, we would have P's, we would have D's, and in order to get 6 regions, we would start with the S's, 1, 2, 3, 4, 5, 6. We would have to pull 2 D's into the system, so that would be S, P3, D2. Right. For iodine pentafluoride, right, iodine would give us 7, 5 fluorines would give us 35, that's 42. We have to draw our connected structure. Our connected structure would look like that. Each bond is 2 electrons, so we've accounted for 10 more, which leaves us 32 to distribute beginning around our fluorines. So when we put 6 more electrons around each fluorine, that's 30 more. That leaves 2 left. The only place to put those 2 is somewhere on the central atom, giving it 6 regions of electron density. Right? So overall, it's going to be octahedral. But what would that look like when we draw it in 3 dimensions? So here's the shape we would get, right? We would put an unshared pair in for one of the bonds in our octahedral structure, right? And if we orient that so that it's down, we can sort of see if we connect this, we get a triangular side. And if we connect that one, we get a triangular side. If we connect that one, we get a triangular side. And so that's where we get the square pyramidal description of the bond geometry and shape. And if we were going to talk about the classical interpretation of the hybridization, in order to get the 6 regions, again, it would be S, P3, D. Here we're going to consider Xenon Tetrafluoride. Again, xenon gives us 8. 4 fluorines gives us 28. That's 36 electrons. When I draw the connected structure, those bonds represent where 8 of those are, leaving us 28 to start distributing around the fluorines. When we distribute them around the fluorines, that accounts for 24, leaving us 4 left. Right? Those have to go around the central atom, giving us 6 regions of electron density, making this octahedral. So what would it look like in 3 dimensions? So if we draw the structure and get the unshared pairs of electrons, because remember, they squeeze closer to the atom, so those 2 regions need to be farther apart. The way to get them the farthest apart is to actually put them opposite each other on the xenon, which leaves us, right, if we connect our fluorines, right, they're all in the same plane. If we were looking at it from above, it would look square, and so that is square planar. And sp3 D2 in the classical interpretation. In the iodine trifluoride, 2 minus anion, right? Iodine would give us 7, 3 fluorines would give us 21, and the 2 negative charges would give us 2 more, so that's 30 valence electrons. When we draw the connected structure, that accounts for 6 of those, leaving 24 to distribute. When we distribute them, that's 18, leaving 6. So we have to put 3 pairs on the central iodine. Again, that's going to make it overall octahedral. if we try to draw that in 3 dimensions, it's a little tough, but we get, right, one electron region geometry opposite the fluorine, right, one in front, and one behind at 90 degrees, but it still ends up being T-shaped. And with the xenon F2, 2- ion, that gives us 24 electrons to distribute. The connected structure accounts for 4, leaving us 20. When we distribute them around the fluorines, that gives us 12, leaving us 8 that we can distribute in 4 pairs around the xenon. And so we end up with a structure that looks very much like this, where we've got, right, around our equator, 4 regions of electron density. Right, the 4 regions of electron density are square planar, but the orientation of the fluorines from each other would be 180 degrees, and so that would be a linear structure. Now, right, by tradition, right, we cover up to 6 regions of electron density, right? But that is not the limit, right? And I'm going to show you some examples. We're not going to have to draw them, but show you some examples of hypervalent species with central atoms with more than 6 pairs of electrons around them, right? So there is an Iodine Heptafluoride, right? That, if you draw that out, it would give us 7 regions of electron density. And so that kind of structure creates a 5-membered equator, so it's pentagonal. Up and down makes it pentagonal bipyramidal. Okay? And so in that pentagonal bipyramidal structure, we get 90-degree bond angles between the axial bonds and the equatorial bonds. If we divide our 360 degrees by 5, that gives 72-degree bond angles between the bonds on the equator. Okay, so we can have a pentagonal bipyramidal structure. Xenon will create an octafluoride 2- anion, right? So that gives us 8 regions of electron density. That creates a structure that we call square antiprismatic. It's a little hard to see here, but if you look from above, right, if one square is oriented this way, then the atoms on the bottom are oriented this way. Right? So you get that square antiprismatic structure. You can create a rhenium nonanhydride dianion, right? That creates a structure called a tricapped trigonal prism, which is a little hard to see. But it took me a while to realize it's 3 trigonal planar structures, right? So if you look at that atom, and that atom, they create a trigonal planar structure, right? Then if you take that atom, and that atom, that's a second trigonal planar structure. And then that atom, and that atom, that's a third trigonal planar structure. So it's like 3 trigonal planar relationships superimposed where each one is rotated 120 degrees from the previous one. Right? So if you rotate that, it's 120 degrees, and then you rotate back up there, 120 degrees. Okay? So we can have 9 things around the central atom. Right? Here's the most extreme one, right? So here's a uranium hexanitrate dianion. Now, since, right, that's 6 negative charges there, that means uranium has to start in a 4+ oxidation state here. But it coordinates with each of 2 oxygens from each nitrate. So if there's 6 nitrates, that's 12 coordination sites. Right? So we have 12 direct coordinations with the central uranium atom. Okay? So that was the highest one I was able to get a good picture of. Right? Now you might wonder, right, why are we worried about these hypervalent species in organic chemistry? Right? Because carbon only makes 4 bonds. Right? Why do we have to worry about any more than that? Well, we do encounter some hypervalent species. One of the things that we will see later in our reactions of alkenes, right? So when we're reacting alkenes, is a reaction of alkenes catalyzed by something called Grubbs catalyst. And so in Grubbs catalyst, there is a ruthenium with 1, 2, 3, 4, 5 things attached, but clearly there's, right, an unshared pair over there because it's creating a skewed, right, it is clearly square planar. Right? That's the center, right? 1, 2, 3, 4 atoms in a plane, 1 above, right? There is our square planar. It's just the steric strain is sort of pushing these down to squeeze it down a little bit. But that's a square planar structure. Right? And there's a reagent that is used for oxidizing alcohols called the Des-Martin periodinane. Now, the Lewis structure eliminates an unshared pair of electrons on that iodine, but when we look at the 3-dimensional structure, we can clearly see, right? If we look at this, 1, 2, 3, 4 atoms in something close to a plane, carbon above it, right? Again, we've got something here which is square planar, a hypervalent species. Right? Since most of us are taking organic chemistry to understand biochemistry, let's look at a couple of biochemical examples. Right? If we look at vitamin B12, right, here we have a cobalt, right? We have a cobalt atom in the center, and then it is coordinated to, right, 1, 2, 3, 4 nitrogens, and they're in an aromatic structure, so they're all in the same plane. There's an R group, which can vary depending on the type of vitamin B12 we're working with. And then there's another nitrogen below. So that is 6 coordinations. That is going to be octahedral. Right? And we can see it here, right? So we've got nitrogens, nitrogen, 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 right? That's 4 coordinations. We've got whatever atom appears directly above it, And then we've got the nitrogen below it. That's 6 coordinations. That's octahedral, a hypervalent species. And we get a similar structure if we look at the heme in myoglobin, which is the protein that binds oxygen in muscles, and hemoglobin, the protein that binds oxygen in the blood. Right? We've got our central atom. Right? Around it is 4 nitrogens. Right? Below it is a nitrogen, and then above it is the oxygen. So that iron in hemoglobin is hypervalent, and it is octahedral. So we do need to be able to recognize hypervalent species in organic chemistry.